Hey guys, welcome. Yeah, so I hope everyone is safe and well. Pray to Jesus Christ. He's amazing. I love him and he will protect you. He'll be there for you. But otherwise, a little bit ago, I made a video to help you prepare for the AP Calculus BC exam coming up soon. And in that video, I specifically focused on two topics. One of them is the Taylor series and therefore a Maclaurin series. And the other is about the ratio test in the category of series convergence. And of course, the ratio test has to come along with it, the harmonic, alternating harmonic, and P series, right? Okay, cool. But after saying in that video that I wasn't going to make another video, I thought a little better of it. I thought it might be a little bit helpful to you if I made this second video that will cover more diverse topics that will still nonetheless be on the narrowed category of topics that will be on this year's exam. Speaking of which, let's look at the AP topics and figure out what will be on this year's exam. Now, this is a document that's available online, so you can look yourself and figure out what topics will be on there. But clearly, these first so many topics are AB calculus topics that will be there, right? You're accountable for these if you're a BC student. But in this video, we're specifically going to focus on L'Hôpital's rule as a part of a question I will help you solve. And all of the questions I'll help you solve, of course, come from previously administered AP Calculus exams and FRQs, right? Okay, so one of the questions will have as its part L'Hôpital's rule, so look out for that. I will make a video that I will share soon specifically about Euler's method. And now, a while back, I already made a video explaining how Euler's method works, and I gave you an example, but maybe that was a bit pitched at an advanced level, so I'll break it down some more in this second video I will share shortly. Okay, other than that, as you can see, the BC topics are highlighted in purple, and some ideas are tossed out, right? Some ideas will not be there. One of the ideas that will not be there is Unit 9. All of Unit 9 will not be on this year's exam. And in Unit 10, it's specific things you're responsible for, accountable for. And those are, well, obviously you need to know the broader definition of convergent, divergent, infinite series, and then the infinite geo must know this, but 10.3 won't be on there. 10.4 will not be on there. Harmonic and P series, they have to be there because, well, they can't ask you questions about radius and interval of convergence without the endpoint analysis reducing to the harmonic, alternating harmonic, or the P series. So 10.5 definitely will be on there. 10.6 no, 10.7 no, 10.8 yes. Determining absolute and conditional convergence. This is like almost like an item of definition. It's not very hard, but you'll be responsible for it. And I already have videos on all of these, right? I have videos dedicated to all of these topics and discuss them in great detail. But of course, this is just a cumulative review. So 10.9, you need to know. 10.10, no, you don't need to know that. And what else? Taylor and Maclaurin, yes, absolutely. 10.11, you need to know. 10.12, no. 10.13, very important. That's why my first video focused on that. And 10.14, definitely. Wait, I said 10.11, finding Taylor polynomial approximations of functions. Yeah, 10.11 and 10.14 are basically like one topic. We can make one giant topic out of them. What you couldn't see, if I could lift it, yeah, I could lift it, is representing functions as power series. Yeah, definitely. That's basically like in line with Taylor and Maclaurin series, so there. Alright, so this is the broad overview of what you're responsible for. There are other things that I didn't comment on, although, for example, I did say Unit 9 will not be on it, and you don't have to worry about it. For the rest, you should do your own research as to what you're responsible for. You're pretty much responsible for the rest of everything else. Alright, enough said. Let's get started. So the first question I want to see with you, and let's title it, the first question I want to see with you is this question. Yeah? Okay, and this is, just to cite the source, this is from the 2014 APBC FRQ. So take a moment to read it, pause the video if you need to, but let's get started ASAP. Okay. So in part A, what you're asked to do is find the value of r, so the radius of convergence, and I'll actually do this in red. Yeah, okay, so radius of convergence automatically means ratio test, unless you know that the series is geometric, therefore an infinite geometric series. The only other way you can answer questions about radius and interval of convergence is to do the ratio test. So the majority of questions, well, 100% of them are about the ratio test, as long as they are about convergence, interval of convergence or radius of convergence. Okay, again, the only exception is you can get around the ratio test if your series is geometric. As you can see, we're going to have to do that in part C, so we'll cross that bridge when we get to it. But first, to find the value of r, well, remember, whatever is inside of sigma, that's a sub n, always. And so the ratio test said that, like, if the limit is n goes to infinity of the absolute value of, I probably want a ruler because otherwise I'm going to be annoying drawing and redrawing my lines. Neat freak. Okay, if the limit is n goes to infinity of the absolute value of a sub n plus 1, right? A sub n plus 1 over a sub n, if this is less than 1, then the series will converge. Now, remember, one way to identify if the question is about radius and interval of convergence, other than reading the question carefully and seeing that it says that, is by seeing that your series has x's in it, right? Because, well, remember, all these other tests that are not going to be on the test, on the 2020 test, like all these series tests, and like not tests in life, not serious tests in life, but series tests, all these series tests, right? Well, they usually work on series that don't have x's in them. For example, you do the limit comparison, the integral test, all these other guys on series that don't have x's in them. And the ratio test can be used in, on similar series that don't have x's in them. But if they have x's in them, the question is usually about radius and interval of convergence. And so here we're not trying to figure out if this series converges, we're trying to make it converge. And so we know by the ratio test, to make it converge, this here, this ratio, as n goes to infinity, needs to be less than 1 in absolute value. So you write this, right? And then proceed. Okay, well, as I said, a sub n is what's inside of sigma. So what this looks in practice is this, and I'll switch to black. Okay, so in practice, what you're doing is lim is n goes to infinity, right? And then a sub n plus 1, well, if this is a sub n plus 1 means changing all of the n's to n plus 1. Those are all the n's I see. All right, so that means that we have first our absolute value, right? And this is gonna look big, so yeah. So first we have -1 to the n plus 1 plus 1, so that's n plus 2, and then 2 to the n plus 1, sorry, and then divide this by n plus 1, right? N plus 1 here, and then x minus 1 to the n plus 1. Now, so we see that the only thing in the denominator really is this n plus 1 right there. Okay, so let me, use a ruler and make this very clear. Okay, so, shoot, sorry y'all. I don't want to make you watch me use a ruler, but let's do it. Okay, so n plus 1 goes here, and then we need to divide this here, which is a sub n plus 1, we need to divide it by a sub n. Well, again, a sub n is just the inside of sigma. But this is a quotient. Dividing by a quotient is the same as multiplying by the reciprocal, so I prefer to see it that way. Alright, so we do that. Alright, so we go, alright, multiply by the reciprocal of this here. The reciprocal of this here is going to be n divided by, as n is the only denominator in here, it will be the only numerator, divided by what? -1 to the power n plus 1, and then 2 to the n, and then 2 to the n, and what else? Well, x minus 1 to the n. Got it. Okay, cool. This needs to be extended clearly. Then, let's make our ruler vertical. Then, yeah. Okay, so this needs to be less than 1. The fun part of the ratio test where we do a lot of canceling. Okay, first, this fella and this fella cancel to a 2 in the numerator. This fella and this fella cancel to an x minus 1 in the numerator. And then this fella and this fella cancel to a negative 1 in the numerator. Got it. So after cleaning up, what we're going to write over here is lim is n goes to infinity, and then what? Lim is n goes to infinity, and then absolute value of what? Well, what do we have left? We have a negative 2 and then times x minus 1, okay? And these guys do not involve n. The negative 2 times x minus 1, none of them have an n in them. So at this stage in the ratio test, make a habit of separating things that have n's in them and things that don't have n's in them, because as you can see, the limit only affects items that have n's in them. All right, got it. Okay, so then we go n over n plus 1, right? And this is the item that will be affected by n going to infinity, okay? And this is less than 1. Okay, as n goes to infinity, this is a pre-calculus like problem. As n goes to infinity, this here goes to 1, clearly. And so after executing the limit, what we'll have is we'll have absolute value of minus 2 times x minus 1 is less than 1. Okay, then using absolute value rules, namely absolute value of AB is absolute value of A times absolute value of B. Using this, we know that we can next write absolute value of negative 2 is just 2, and then times absolute value of x minus 1 is less than 1. Dividing both sides by 2, we see that the absolute value of x minus 1 will have to be less than 1/2, meaning we are done in this problem. Okay, so R, the radius of convergence, is equal to 1/2. So we answer the question by saying R is equal to 1/2. Got it. Now, look here. So this question ended a little early because it's not about the interval of convergence. If it was about the interval of convergence, you need to interpret this as saying negative 1/2 is less than x minus 1 is less than positive 1/2, then add 1 to all three parts, and next write that this is 1/2 is less than x is less than 3/2. 3/2 starts with a 3 on top, right? Okay. And then you could, like if you so chose, draw a number line real quick, right? Like you could draw a number line just to convince yourself, in fact, we have found the correct radius. You could be like, all right, so here's a number line, and if we put 1/2 over here, sorry, I'll write it on top, why not? We're allowed. 1/2 over there, and then 3/2 over here. Clearly the middle is 1. Notice that the middle is the center of your series, right? X minus 1 here is telling us the series is centered at x equals 1. It also says it over here. But anyway, we have 1 right there, and so we're half a distance, length of 1/2 on either side of 1, and therefore the radius is 1/2. Okay, we're convinced. But yeah, what would happen if the question was about the interval of convergence is now you need to take the endpoints, these guys, and plug them in for x individually, and then analyze the resulting series, which clearly will not have an x in it, and will invariably turn into the harmonic alternating harmonic or p series. So that's all that. All right. Okay. Cool. Now, real quick, let's move on to part B. I might accidentally this tool, like it took a while to get used to, and like I had to learn layers and such, and I didn't want to accidentally delete that. But anyway, let's go to part B. Part B says, hopefully you've read it. It says, find the first 3 non-zero terms in a general term for f prime. Okay, this is f, right? And so one way to find the first 3 non-zero terms is to figure out the first 3 or 4 non-zero terms of f and then to take their derivative. But because the question also asks for the general term of f prime, what might be smarter and more efficient is to take f's general closed form and to take its derivative, right? And so since this here is f, what we can do is be like, oh, f prime is just its derivative. And notice then that finding f prime in closed form amounts to doing this. Well, we go n equals 1, so the limits on sigma for f prime are not going to change. They're going to be the same as f. And also this -1 to the n plus 1, it's going to stay. And so will the 2 to the n. And so will the n down here. Now, I'll explain a little bit more why these guys stay in the derivative. And so then the derivative only affects this part I'm saying. So that part is going to turn into n times x minus 1 to the power n minus 1. And of course, there's a little bit of tidying up you could do. Specifically, you can cancel this fella and this fella, right? And when you do, f prime is going to turn into this here, right? Okay, so n equals 1 to infinity, and then -1 to the power n plus 1, and then 2 to the n, and then times x minus 1 to the n. Okay, to the n minus 1. Okay, cool. Now, why is it that this -1 to the power n plus 1 and this 2 to the n over n, why are they going to stay when we take the derivative of f? Well, here's why. Let's just plug in n equals like 2 and look at a single term in this, right? So for f, when n equals 2, what we have is, well, we're only looking at a single term, so we don't need to look at sigma. -1 to the third, so it's going to be negative, and then it's going to be 2 to the third over 3, and then it's going to be x minus 1 to the third. Take the derivative of this. What are you going to get? You're going to get that the derivative of this is going to be -2 to the third, and then over 3, and then times, 3 times x minus 1 to the second. You follow? So like these guys, they weren't touched when we took the derivative of a single term, so that's going to be true for all the other ones, right? Okay. Cool. And so that's why we left them where they're at. All right, so we've answered part B. Well, we've answered the question of the general term, because remember, the general term is just what's inside of sigma. So as far as the general term of f prime, it is this fellow right here, right? And of course, now that we've got that, we can easily find the first 3 non-zero terms. We just plug in n equals 1, n equals 2, and n equals 3. So when n equals 1, we get -1 to the second, which is +1, and then 2, and then x minus 1 to the 0th power, 1 minus 1, so we just get 2. When n equals 2, we're going to get minus, it's going to be -1 to the third, and then it's going to be 2 squared, or 4, and then times x minus 1 to the 2 minus 1, so there that is. And then next is going to be +8, and then it's going to be x minus 1 to the third. Yeah? Okay, cool. All right, so this completely answers part B. Part C, it says, the Taylor series for f primes about x equals 1. Well, yeah, it's the same center as f. Found part B is a geometric series. Remember, the infinite geo is very, very, very important. It's a geometric series, they say, okay? And it says, find the function f prime to which the series converges in the same radius of convergence and the same interval of convergence as f, right? Okay, cool. And we have to find f. Okay, that's quite a bit, but it's not there. It's not that hard. It's not very hard. So first, let's delete this and say that this is part C. I'll keep this because this is f prime, right? But yeah, so this is part C, and maybe we write it right here. Okay. So for part C. Oh yeah, and this is from part B also, so we don't need it over here. Like, let's have it up there. Fine, got it. So, part C, yeah, f prime this, which is in first 3 terms this, they say is an infinite, well, it's a geometric series, they say. Well, it can only converge if it's an infinite geo where the absolute value of r is less than 1. So remember, a geometric series is one where like you start with some number or some term. It doesn't just have to be a number, it could have x's in it, and then, well, you're going to get AR and then plus AR, whatever the item A may be, right? It could have variables in it. You're going to get AR squared and then AR cubed and yada yada, right? And we know that the infinite geo, I have many videos in my pre-calc videos on this. The infinite geo, we know, converges when the absolute value of r is less than 1. Remember, r is the item that you're multiplying by to get from one term to the next. So we know the infinite geo converges when the absolute value of r is less than 1, and it converges specifically to a over 1 minus r. And so it is this formula that we need in order for us to say what the function f prime is, because supposedly f prime, this here, is an infinite geo. Well, we can clearly tell it's an infinite geo if you think a little bit about this, because Well, to get from the first term to the next, what did I do? I multiplied by minus 2 times x minus 1. And to get from here to here, I multiplied again by minus 2 times x minus 1. Now you have the security of them telling you it's a geometric series, and so you only really need to look at the first two terms to figure out what r is. But what I just said is that r, in this specific case for part C, r is equal to minus 2 times x minus 1. Alright, got it. So then, a is just the first term, and so the first term is 2 for f prime, right? And so we know that it has to converge it has to equal, f prime has to equal, let me write it in black, I suppose. F prime has to equal f prime has to equal a, which is 2 over, and then, yeah, good, that's horizontal. It's 2 over, and then 1 minus r, which is negative 2 times x minus 1, yeah? Okay, cool, got it. Now, it converges to this, f prime converges to this whenever this is true. So when the absolute value of minus 2 times x minus 1 is less than 1. But wait, this means that 2 times absolute value of x minus 1 is less than 1, meaning that absolute value of x minus 1 has to be less than 1/2. Notice that we got here to this interval of convergence by using the requirement for the infinite geo. But earlier, we had gotten to the same interval of convergence and the same radius of convergence for f by using the ratio test. So this is what I was saying earlier about how, like, the only time you could avoid the ratio test for radius and interval of convergence is if your series is geometric. Yeah? Okay, cool. Now, we should probably simplify f prime a little bit more, because in the next part they ask us to find f. And so obviously we're going to have to integrate f prime to get to f, right? So we have that f prime is, if you simplify correctly, the minus is going to give us a 2x. Well, this is a plus basically, and then you get minus 2 plus 1, so it's minus 1. So this here is f prime as a function. Isn't that what they said? Find a function. Yeah. Okay. So now we don't need all of this junk, and we just need to figure out f, and we are done with this problem. So let's do that. Let's write precisely that. Okay. I love math, but I talk about it like way too much. It's like it occupies so much of my day, but thank Jesus I love it, because if I didn't, oh man. Okay, so this goes integral, right? Like, because they said find f, and integral, and then it's 2 over, and then it's 2 over 2x minus 1 dx, and so we could take the 2 in front, the constant, right? Like, so let's do precisely that. And then otherwise we could write a 1 here, and this is pretty straightforward. Well, I already okay, so this is going to be 2 times the natural log of absolute value of 2x minus 1 divided by 2. And if you want to know why I have to divide by 2 here, do a mini u substitution. If you let u equal 2x minus 1, du is going to equal 2 dx, and then so dx is going to have to equal 1/2 du, and so this 1/2 explains why I must write that 2 right there. Okay, but you know, I'm not going to teach you u sub. You should know that. You should have known that without me pointing it out. But yeah, okay, so clearly we could simplify a little bit, and that little bit of simplifying is this, and write a plus c here, and you are done. Yeah, okay, cool. So we're completely done with this question. Let's move on to the next. Okay, and this question is from the 2017 AP BC FRQ, and I believe it was problem 5. The previous question was problem 6 on the 2014, in case, you know, wanted to test my memory or something. All right. So read this question and let's get started. So f is this function. Find the slope of the tangent line to the graph of f at x equals 3. This is pretty straightforward, so we need to find f prime. So first let's write f so that it's friendly to take the derivative of. That way we avoid the quotient rule, and that means that we write it as 3 times 2x squared minus 7x plus 5 to the negative 1 power. Got it. And so then f prime, the derivative, is going to be minus 3 times 2x squared minus 7x, and then plus 5 to the negative 2 power. Got it. And so cleaned up a little bit, f prime we're saying is equal to whoa, I'm not done with f prime. I forgot chain rule. I need to multiply by the derivative of that. And so that is 4x minus 7, right? So f prime is going to be minus 3 times 4x minus 7, right? And then all of this divided by okay, divided by 2x squared minus 7x plus 5 to the second power. Now, I don't like that parenthesis. Okay, to the second power. And this one isn't much better, but I'll live. Okay, now look here. So to find the slope of the tangent line at x equals 3, you just need to plug in 3 into this expression. Now, I'm not much of an arithmetic fan, so I'm not going to do that. I'm going to keep it moving, but you do that. Okay, part B. Find the x-coordinate of each critical number. Now, crucial is that like a lot of kids forget that critical numbers are also places where the derivative is undefined. So kids are quick to realize that critical numbers are where f prime is equal to 0, but also where f prime is undefined. So in critical numbers, we're saying we need to figure out f prime is equal to 0 and f prime is undefined. Okay, I said that I think 3 times, you should know. So f prime equals 0 or undefined. And now a fourth, so f prime is equal to 0, obviously, where this numerator is equal to 0. And so we divide by negative 3 on both sides after we set the numerator equal to 0, and all that we'll have is 4x minus 7 is equal to 0. Now, that means that x is equal to 7 over 4, which I believe is like 1.75, right? Okay, cool. This is 1.75, and this is in the no calculator section as it is problem 5, but no problem. This is simple arithmetic you should know like in 3rd grade. Okay, and now we need to figure out where f prime is undefined, which means we set this denominator equal to 0, right? And so we need some factoring skills. I have a lot of videos on factoring quadratics where the leading coefficient is different from 1. So quadratics where the leading coefficient is 1 are called monic, but that's just me showing off. So like, alright, so watch those videos if you need to learn how to factor this, but it's going to be like, what numbers multiply to 10 and add to negative 7? Negative 3 and, add to negative 5 and negative 2. So, and then minus 2x, and then minus 5x, and then plus 5. So I just rewrote this quadratic so that the middle term is split, and so that now we can group factor, right? So when we group factor from the first 2, we could take out a 2x, and so we do. And then we're going to get x minus 1, and then from the next 2, we take out a minus 5, and we're going to get x minus 1. So we see that it factors as x minus 1 times 2x minus 5 is equal to 0. Okay. Well, it factors like that, but then we want to know where it's equal to 0, so we do set it equal to 0, because, well, that would be places where the derivative is undefined. So that's x equals 1, and then x equals 5 over 2. Those are endpoints of the interval. See, I don't even know if you were paying that much attention, but I was. So the endpoints are not included. Okay, so the only critical number that we need to worry about is this. And they say classified as a local min, local max, and whatnot. Okay, so for that part, all you need to do is draw a number line for f prime and test points on either side of this number line, right? Like, so, well, test points on either side of the critical number on this number line. Okay, so this number line is for f prime. Sorry, I'm talking really, really fast so that I get this done ASAP so that I could do other things that I really need to get done. Okay, 7 over 4. All right, got it. So if you test a random number to the left of it, what could that number be? Like, I don't know, like 1. And then, so if you plug in 1 into f prime, what are you going to get? You're going to get, let's see, negative 3. And then this part is going to be negative. So you have a positive in the numerator. And the denominator is just going to be like positive at all times because we're squaring it, right? So you get positive over positive, so that's positive. And then to the right of 7 over 4, we can plug in 2. If you do, now it's 8 minus 7, so that's positive. So the denominators I've already said is going to be positive because it's a squared quantity, so you have negative times a positive, and so that's negative. Negative over positive is negative, so it goes from positive to negative, meaning it's a local max. So it's a relative or local max, and that's that, and I just justified it, yeah? Okay, cool. Now, next is part C. So let's go to part C as efficiently as possible. Okay, so part C. use the identity, cool, so that they just, oh man, I could have seen how this is factored if I just like glanced at the next part, right? Like, okay, well, now you could double check me. So basically in this part, they've done the partial fraction decomposition part for you. So all you have to do is just do the integral, right? Like, and so use this identity to evaluate. All right, so we have an improper integral, and we know that we need to use proper grammar, meaning limit is n goes to, and well, I could use n, but probably better if I use a. Now, to stay consistent with other videos where I've shared many improper integrals, some of them very hard, right? Okay, so check out those videos, but yeah, this is going to be like now 2 over, and then 2 over what? 2 over, and then 2x minus 5, right? Okay, 2x minus 5, and then minus, right? And then 1 over x minus 1, got it. Okay, so 1 over, okay, x minus 1, and then dx, right? Okay, cool. So this is going to say lim is a goes to infinity. This proper grammar requirement, by the way, is because infinity is not a number. So after you finish the integral, you can't plug in infinity. So you have to recast it as a limit. Anyway, the first part is going to be, well, just the natural log of the absolute value of 2x minus 5. And you should know why there's no 2 in front of this, because we've done a problem where, like, I showed you by like chain rule it canceled in the previous problem, right? Okay, and then you have minus the natural log of absolute value of x minus 1. Now, this we're going to evaluate from 5 to a, right? Okay, so when we plug an a in it and then use the log rule that says that like log of like something minus log of something is equal to, well, okay, star and plus, or no, like a sillier star. This is same as first star over sillier star, right? Almost imitated that, right? Okay, so we use that. Kind of looks like a 4, but whatever. Okay, so we use that rule, and when we do, what we're going to get, or we're going to have to write next, is lim is a goes to infinity, and then it's going to be the natural log of what? The natural log of the absolute value of, okay, the natural log of the absolute value of, and then it's going to be 2a minus 5 divided by a minus 1, right? And then minus, we plug in 5, so the natural log of absolute value of, cool, I wrote it, okay, so 10 minus 5, which is 5 over, and then 5 minus 1, which is 4, right? Okay, cool. Now, as a goes to infinity, what we could do is write this as the natural log. This is a little, like, used but really important limit law, which is that, like, we could, I'll write it in its full glory in a second, which is that we could take the limit inside of the ln. And so this is very formal, you don't have to do this, but if we write this, it's going to be 2a minus 5 over a minus 1. It's obvious that this limit goes to 2, right? Okay, so it's like for large a's, like subtracting 5 and subtracting 1 don't really matter, and so we're going to get 2a over a, and so that's just going to be a, right? So this part is going to be natural log of, 2a over a, that's just going to be 2. This part is going to be natural log of 2, and then we'll have minus natural log of absolute value of 5 over 4. So putting together what I just said, we'll have ln of 2, and then minus ln of 5 over 4, but then using that log rule once more, we could write this as ln of 2 divided by 5 over 4. That's the same as multiplying by 4 over 5, so 8 over 5. Yeah, okay, so it does converge, and it converges to this number. Now, the next question is kind of really silly. I wanted to keep it so that you know that it was a part of this test and a part of this problem, obviously, but it says, say if the series converges or not. Well, this series is identical pretty much to the integral, so this is a series version of the integral, right? Like, and so then they're hinting at using the integral test. And so we would say that the series converges by the integral test, but remember, on the list of topics I showed you earlier, we'd said, maybe we didn't, but I'm pretty sure we did, that the integral test will not be on it. The only things on it from series convergence are, well, the general definition, geometric, and then p, and then harmonic, alternating harmonic, and then the ratio test, yeah? Okay, cool. So, of course, Taylor Maclaurin, but that's its own category. All right. So, next is, well, the next question. Okay, so, what is that? This is a question that a student shared with me, and I don't know what FRQ it comes from. I've looked in all the recent ones, I haven't found it, but it's a really, really important question to review, and obviously the way it's written is very much like any FRQ, so you can tell that it's an AP question. It's definitely an AP style question, so read it and let's get started. So you have a function f given by this. Write the first four non-zero terms in general term for Taylor series of f about x equals 0. So they're saying the Maclaurin series, right? And also, I need to get a sip of coffee. Hold on. Also, what is it? Yeah, like, we know the definition of the Taylor series, so it's tempting to use that. But remember, we could get like new series from well-known series, right? And so you shouldn't reinvent the wheel. The way you should do this is by modifying the Maclaurin series for the natural log, modifying the Maclaurin series for your best friend. Okay, so this is a question that a student shared with me. It's very, very obvious that it's an AP style question and it's from an AP, but I've looked through all the recent APs and it's not one of them. So I don't know where it came from, and therefore okay, so this is a question that a student shared with me, but I don't know which FRQ it comes from. I've looked through all the recent ones, so it's not from one of the recent ones, but it's pretty obvious that it's an AP question because it's very much an AP style question and a very important practice for you, and therefore why I'm sharing, obviously. Okay, read it. It says in the first part to find the Maclaurin series. Yes, Taylor series centered at x equals 0. For what? For f. Okay, cool. Now, it might be very tempting to use the definition of the Taylor series, right? And that, by the way, you need to have memorized. And that is, I'll write it very quickly, that is n equals 0 to infinity of fn, the nth derivative of a over n factorial, and then x minus a to the power n, right? So this is a general definition. Of course, when a is equal to 0, it becomes the Maclaurin series. Now, it's tempting to use this and find a bunch of derivatives of this. Notice that it's not fun to find derivatives of this fella. So what are we to do? Well, remember, you could always take derivatives of certain Maclaurin series to get other Maclaurin series. You can integrate them, but you could also modify them. So that's what I'm talking about. So other than the general Taylor formula definition, right, or the Taylor series definition, it's not really a formula, it is kind of, but it's a definition. So other than using the definition, remember, or memorizing the definition, one of the other things that you need to memorize, in fact, this is a must know, is the infinite geo, right? Like, and I already talked about the infinite geo at least once here, and so this should not be surprising at all. But the infinite geo is the series that you must know for the AP is 1 over 1 minus x, and this is just very tidy and simple. It's n equals 0 to infinity and then x to the n. The other thing you should have memorized, and yes, I know, you get to have an open note test this year, but you should nonetheless memorize these things because you're going to be timed and you're going to waste time looking these up when you should just commit them to memory. Kids in the past had to memorize them, so you should also. Anyway, the third item that you must memorize, I suggest, is the e to the x Maclaurin series, and you should know that. That's very simple, but let's stay focused. So we need this in this problem. Why? Well, because I could first write that f of x is equal to, it's 2x, and then times, it's 2x times what? Times 1 over, I'm breaking down f of x, this same f of x, 1 over, and then I'm going to write 1 minus negative x squared. Well, obviously that's going to read 1 plus x squared in the denominator, but this is nice to break it up because what I could see now is I could take this and substitute for x right there, meaning I substitute for x right there, right? Okay, so when I do this is what I'm going to get. First, I'm going to get that 1 over 1 plus x squared is going to equal, n equals 0 to infinity, and then of negative x squared to the n. And whenever you get a negative item to the n power, make a habit of breaking it up as -1 to a power, as I'm about to do. So this is -1 to the n, and then otherwise x to the second to the n. X squared to the n is the same as x to the 2n. So better we write it that way. Cool. So the only other thing that we have left to figure out what f is, right? Look at how efficiently we're doing it. Is to multiply by 2x. So multiplying by 2x right there means multiplying sigma by 2x right here. Feel free to keep the 2 outside sigma because we're allowed, but otherwise multiplying by x right here means that I change the exponent on x to read 2n plus 1. So I'll account by this this plus 1 here on the exponent for multiplying by this x. Right? Okay, cool. We're done. We just figured out what f of x is. It's right here in its full glory. So let's get all the nonsense in between out the way, and I'm sure we're going to need this for some parts. So let's isolate f, and which is right here, right? Okay, and like, yeah, tuck it away somewhere. Okay. So shrink it too. All right, so there's f. Got it. Don't need to. Okay, 75% is good enough. There it is. All right. Oh yeah, 75% is good enough for the AP also. I was talking about like the size of this when I shrank it, but anyway. B says, does the series found in part A when evaluated at x equals 1 converge to f of 1? Explain why or why not. See, I told you we're going to need this. So when x is equal to 1, this series is going to turn into what? It's going to turn into, when x equals 1, so this is part B. It's going to turn into n equals 0 to infinity, and then it's -1 to the n, and then 1 to the 2n plus 1. 1 to any power is just 1. So this is what we're going to have. Oh, okay, well, kind of anticlimactic, but pretty fun. So does this converge or not? Well, it's an alternating series. Remember, the alternating series test is not part of this year's AP. I have videos, a number of videos, 4 videos I think, on the alternating series test, and the first one discusses why it works the way it does. And so in that video you should watch and learn that, like, this is kind of how the alternating series test works, or why it works. Not kind of, this is why it works. So like, suppose that you have a particular series. Let me erect the x and y axes, right? Okay, so like, let's say that this is the y-axis and the x-axis further down below. All right, so this is what we've got, right? So like, let's say that this is the x and this is the y-axis. Now, a particular alternating series that we know, the alternating harmonic, believe it or not, converges to the natural log of 2. I have a video showing why it converges to the natural log of 2. But yeah, so some alternating series converge, right? And they converge to a specific number. Like the alternating harmonic, as I just said, converges to the natural log of 2. So let's call this number that the alternating series converges to s. So if we call it s, this blue line is showing that it's the number s, right? Now, the way the alternating series test works and how alternating series converge is if this is n equals 1, right? Then, like, when you evaluate the series, like, the first partial sum will be, like, s1, let's say, is over there. Remember, partial sums are like when you add up to when you add up the first n terms. So s1 is simply a1, where again an is what's inside of sigma, and so then s2 then naturally is a1 plus a2, and s3 is a1 plus a2 plus a3. Now, because they're alternating, if the first term was positive and so it was up here, then the second term, when you add to the first term for s2 when n is equal to 2, is going to bring you down below the value of s. So it'll be over here, but it will get closer to s, right? And then the third will get, when n is equal to 3, will be on the other side, but it'll get even closer. And so they eventually, like, get arbitrarily close to the number s, and so they converge to the number s. That's when they converge. So does this one converge? No, because look at s1. S1 is just the first term. That's when n is equal to 0. So s1 in this case is like a0. That's the first term, right? When n is equal to 0. That's why I'm calling it a0. Feel free to call it a1. Anyway, that's -1 to the 0. Well, that's +1. But s2 is when n equals 0, which is +1, plus when n equals 1, which is -1. So this is 0. And then S3 will be like, well, it's going to be S2 plus A3, right? Or it might count since the first term is A0, it's going to be A2 actually. And so now we're going to add positive 1. Well, so we're going to have positive 1. And then the next will be 0. So what's happening is like, let's say that like S is some value in between and this is positive 1. So we have, in this particular series, it goes to positive 1 and then 0 and then positive 1 and then 0. There's no way to, sorry, hold on, 0 isn't there, it's for the next n, so over here. And then positive 1, I was just excited to say the next bit that I was going to say, which is that like there's no way to reconcile. They're not getting close to some value in between. They're just like staying where they're at and just bouncing around. So no, the answer is no, it doesn't converge to f of 1. And f of 1 obviously is like when x is equal to 1, which is what they said to do in this part. Yeah, okay, they said explain. Was that explanation enough? I thought so. Okay, so let's keep it moving. Alright, so what is next? Next is this. Part C. The derivative of ln of 1 plus x squared is that. Yeah, well, feel free to check. They didn't even have to tell us. They should have asked you to come up with this on your own to see that this is the derivative of ln of 1 plus x squared. So it says, write the first 4 non-zero terms of the Taylor series for ln of 1 plus x squared about x equals 0. They don't ask us for the general term, but they ask us for the first 4 non-zero terms. I'm still going to work on the general term for ln of 1 plus x squared, and I'm going to get the first 4 non-zero terms from the general term. Okay, the general term, remember, is what's inside sigma. Now, since this here is the integral of our f of x guy, I'll just write this is the integral of f of x first. And so then that means even if this is unusual for you, we can integrate the series. So, you know, the integral allows us to write a constant in front, so I'll write that. Otherwise, I'm going to have sigma n equals 0 to infinity, and then this is a more interesting way of going about it than otherwise, and then plus 1, right? Okay, now remember, sigma just means add. So if I have a bunch of things added, like let's say f1 plus f2, like their functions, plus f3, and I'm calling each of the terms here functions, and on and on and on. If I have the integral of all of them, well, I can give them their own individual integrals. So that means that sigma won't care if I put the integral sign in the inside of sigma, right? So by the property that I just cited, what I could do is like, well, I could keep the 2 out, but I'll change that sigma sign to go inside. Okay, now for reasons I've already explained, the sigma, the integration is not going to affect this negative 1 to the n power, right? So I could actually put it further inside. Okay, fine. And so then now when I do, I see that the natural log of 1 plus x squared would be, well, it would be 2 times, and then sigma n equals 0 to infinity, negative 1 to the n, and then x to the 2n plus 2 divided by 2n plus 2, which I could write as 2 times n plus 1. Why do I want to do that? Because I'm attentive and I see bingo, yeah? Okay, cool. So then I'm saying these are this is the general ln of 1 plus x squared, and so then we could just plug in for the first 4 non-zero terms, we could plug in n equals 0, n equals 1, blah blah blah, and you get there, right? Okay, cool. Now remember, you could find the Maclaurin series for this by starting off with the Maclaurin series for ln of 1 plus x, which is discovered by plugging in a minus x right there and then taking the integral. And so there's another way to go about it, but that's not what they said here, so we stick to what they told us to do. Alright, well, I'm rebellious. I don't like sticking to what they told us to do. I want to do what I want to do, which I'm doing. Okay, let's keep going. I mean what Jesus told me to do. Okay, now real quick. So there was a part D to this question, but part D was about Euler's method, and as I said at the start of this video, I'm going to dedicate a video to that part, and it's going to, of course, use this differential equation, but yeah, look out for part D in a separate video, but the rest of this, let's do right here. Okay, and this is from the 2016 AP BCFRQ, and it's problem 4. Darn it, I deleted what problem number they were so I could show off about how good my memory is. But like I forgot to delete this one. I'll do it right now. Okay, how good is your memory? Huh? Do you remember what that was? Okay, I'm trying to delete you. Go away. Okay, it's problem 4 from the 2016. Alright, yeah, I'm so funny. Okay, so part A is about the derivative of the derivative. We're given the derivative. So like we just do d dx and then of dy dx, and that's going to get us d squared y dx squared, or the second derivative, d squared y dx squared, right, the second derivative. And that, in this case, is going to have to be 2x minus 1/2, and then the derivative of y is y prime, or dy dx, but read the question carefully. They said, get us the second derivative in terms of x and y, so you cannot leave this in there. So what you have to do is replace it with what we know it is, which is there. And so you go, all right, this is 2x minus 1/2 times x squared, and then minus 1/2 y. Okay, if you simplify all this, what you're going to get is that d squared y dx squared, the second derivative, is going to be 2x minus 1/2 x squared, and then plus 1/4 of y. Okay, now we're going to need the second derivative, and since this is the last problem, I could write any freaking place I want and keep it there. Okay, alright. So part B says, let f be, well, the function whose derivative is this, right, and the particular one, right, that goes through this point. Particular one because, well, there are infinitely many functions whose derivative is this. They're different from one another by a constant. So the particular one is pinned down by telling you a point on the function y equals f of x, right? Anyway, yeah, so, and so we're asked, is -2, 8 a local max, min, or, all right, first, remember from what we've said so far, to establish if it's a local max or min, we need f prime to equal 0 or be undefined. But since f prime here, which is dy dx, does not have a denominator, we know that it's defined everywhere, so we just need to see if -2, 8 is going to make it 0. So we evaluate dy dx at the point -2, 8, and we see what happens. Well, when we plug in x is -2 and y is 8, we're going to get -2 squared minus 1/2 times 8, and so that's going to say +4 minus 4, and so that's going to be 0. Okay, so check. We know we have a horizontal tangent at this point, but then we need to classify it as the local max or min. Normally what we do is what we did earlier, which is like draw a number line and then label it f prime. So I'll go ahead and do that. Draw a number line, label it f prime, right? And then put on our candidate critical number. And so this time it is x equals -2, and then we test the number to the left and test the number to the right into f prime, right? Oh wait, one problem, we don't know the function f. And so since f prime, the derivative, requires both x and y coordinate, if I was to test -3, for example, to the left of this critical number, -2, I don't know the y coordinate for -3, so can't use this. Too bad. So what do we do? Well, the so-called second derivative test will bail us out. What am I talking about? Well, remember, the second derivative test, which, by the way, was on the list of topics that I shared earlier, the second derivative test said if you had a horizontal tangent and then you were concave down, then you're a local max. I could have done that better. I don't like the asymmetry. Asymmetry is of Satan. Okay. I have a book saying that. I don't know if that's true, but I don't like asymmetric stuff. Okay. But if you're concave up, then you're a local min. If you're concave down, you're a local max. If you're concave up, you're a local min. Got it. And concavity, remember, is all about the second derivative, right? Okay, cool. And look at what we've got. Second derivative. So what we could do is plug in the point -2, 8 into the second derivative and see what happens. So when we evaluate this at -2, 8, qu'est-ce qui se passe? I think that's French for what happened. What happened? Okay, so I think that's Puerto Rican. Anyway, 2 times -2. What happened was we get this. Sorry, I'm so silly. I laugh at my own jokes too. Gotta keep life fun, right? Okay, so 1/4 and then 8. Okay, so we get -4, and then what happened was we get -2 and we get +2 and this all turns into -4, right? And so we're concave down because the second derivative at this place is negative. And so if we're concave down and we have a horizontal tangent, we said already we're a local max. All right, so it's a relative maximum. Got it. And then finalement, so appropriate because the next question is about L'Hôpital's rule, but screw L'Hôpital. It's not his rule. It's your rule and my rule. We should get as much credit for this rule as L'Hopital did, because, well, apparently he's a French rich person who paid for it. Some kid told me who it was exactly. I credited to Euler, because Euler like invented everything, so it's Euler's rule. All right, so let's go. How do I know it's L'Hopital's rule? Well, because when we're given a limit, usually what we do is just plug it in to see what happens, and you should plug it in, and when you do, you're gonna write g of -1 minus 2 over, and then what is it over? Over, and then it's 3 times -1 plus 1 squared. And so this is going to be like, well, if you were paying attention, it says g of -1 is 2. So we're going to have in the numerator 2 minus 2, and then over 3 times 0, so that's 0. So this is 0 over 0, which is how I knew we're going to need L'Hopital's rule. It's also because I've done this problem with students I was preparing, like over and over and over. All right. So what does Euler's rule say? Well, it says that we take the derivative of the numerator and then take the derivative of the denominator and evaluate the limit. And we can keep doing this. We just keep taking derivatives of the numerator individually and denominator individually and plugging in the limit point until it works out. So if it doesn't work out, keep doing it until it works out. All right, you've heard of Leah. If first you don't succeed, dust yourself off and try again. So the derivative of the numerator, which is g prime. If you guys are too young for Aaliyah, well, screw you. She's really cool. She's like a hip hopper. Anyway, the denominator is like 6 times x plus 1 when we take the derivative, right? Okay, cool. Now we plug it in. When we plug it in, we're going to get g prime of -1 over 0, clearly, because we still get -1 plus 1 times 6. Who cares that we're multiplying by 6? Screw 6 anyway. I don't like it. I like 7 and 42. Okay, so the denominator is 0. So g prime of -1 in the numerator. This is an infomercial for calculus, by the way. This is not a math lesson. Okay, g prime of -1. Well, how do we do that? Oh yeah, like they said that y is equal to g, so g prime is really equal to y prime, which is really equal to dy dx, right? And so they're saying we can plug in dy dx, but we need x and y. Yes, this here means the same as the point -1 comma 2 is on the function g. Got it. So it means that we could take dy dx and evaluate it at -1 comma 2, and when we do, look at what is going to happen. It's going to be 0. That's my guess. Okay, so we get -1 squared and then -1/2 of 2. Anticlimactic. So it's 0. So 0 over 0. Got it. But as I said, it's going to work out eventually. So do it again. This is not a metaphor or like a simile or like philosophical like thingy. Like it's just like about this problem. Okay, maybe it's not. I don't know. Like, okay, so you go, the derivative of the denominator is now just 6. So we know it has to work out because we don't care what the numerator is. If the numerator is 0, we're going to be like, oh, it's 0, this whole limit. If the numerator is like anything but 0, we'll simplify and say what number that is. Okay, this is going to be g double prime of -1. Man, someone was thoughtful. Now I don't want to write a 6, so what do I do? Well, okay, because then, like, yeah, I would be writing the devil's number. I think they intentionally, like, create, like, situations where you have to write a 6 over and over in these problems. I swear, I'm not paranoid. Like, they literally do that on every problem, because, like, the people who, like, create these APs are controlled by people who worship the devil. And I am a man of Christ, so screw all of them. Maybe that's why Jesus, like, brought about Corona, so they stopped doing it. Listen. Okay. Jesus is gonna keep crushing you bitches until like you actually finally listen, you finally get it. Like you're not in charge. Only Jesus is in charge. Jesus runs this world. Stupid idiots. Okay, anyway, g double prime of 1. Okay, so well we plug in the point -1. My bad. G double prime of -1. We plug in this point into, well, the second derivative, because again, if g is y, then g double prime is the second derivative we found, right? Okay. So if we plug in -1, 2 into it, you do it. Like you're gonna get -3. I've done it. I told you, like over and over. Dilemma. So -3 over that number. So it's gonna be negative. What is that? -1/2, right? That simplifies. Or no, actually, g double prime is gonna be -2. So it's gonna be -2. It doesn't seem like I set it up for that. -2 over that number, which is gonna be -1/3, right? Just so I can say, screw you people who believe in this devil number. Screw anyone who worships Satan and the devil. Like, this is for kids who are bound to be people of Christ and people who are already people of Christ. That's why I'm making this. And if you're a Muslim, I respect you. I respect what you believe in. Anyone who, like, believes in something much bigger than themselves. And by something much bigger than themselves, I don't mean like politicians or these other idiots who think they control the universe. Because, well, they're just people like you. They're not bigger than you. Okay, all right. Point made. Keep watching. I hope you enjoyed this. Take care. Bye.